Right, good afternoon. I don't know what happy Sunday is in French, unfortunately. But this is just a quick recap of what you've been doing and looking at over this week. And the topic has been Petri nets. So I thought we'd just start off by just comparing state diagrams, graph sets and Petri nets, and then a little bit about some properties of Petri nets as well. So in state diagrams, this is the one we looked at a few weeks ago. We have a diagram, and in this particular diagram, only one state is active. So when this transition occurs, this moves from here to here, and the dot indicates the active state. But in a state diagram, you can only have one of these states can be active at any one time. As we go a little bit more complicated to graph set, here this could be the active state. This time though, when we fire this transition, two states become active. So in this case, we had one active state. In a graph set, using these double parallel lines, we can have parallel activities, and so you can have the potential for more than one active state. So what could happen is when this one could move to there, say, and then this one would then move to there, eventually move to here, and then if this one and this one were both complete, this could then complete, and you could go to there, and then you could fire the last transition and go back to the start again. So in this one, just one active state. In this one, the potential for two active states. Now in a Petri net, it's more complicated again than this one, so we can have as many active states as we like in this. So, and the active states now, so we could have, say, these things are called tokens, and we could have, say, we could have more than one token as well. So in a Petri net, you've got a similar sort of diagram to a graph set, except for the fact that we can now have, when you divide up into two, you just divide up into two. When you come back together, you just come back together. So these just become off transitions. But then you can have more than one token. We have tokens in Petri nets, more than one token at any place, and as many tokens as you like as well. So this gives you a much more rich modelling environment than these two. And just coming back to sort of the main thing to know about Petri net is that there are the conditions for moving tokens around the net. So we've got four structures that are worth noting. This is called a normal arc. That's just indicate by a dark arrow. We've got an inhibiting arc by a circle. Enabling arc, an arrow but with sort of the centre blocked out. And also the possibility for a weighted arc as well. That means an arc with a weight on. So in this case I've put 3 on. And in a Petri net, this is a transition, and the transition has to be enabled first and then it can fire. So if you enable this transition, it means it's ready to go, like a gun with a bullet in, and when you pull the trigger of the gun, it fires and the tokens move. And if we looked at this particular one, it's interesting to look at. So say we got a token there, and say a token there, and let's say we got 4 tokens there. So here we've got a condition now. So this one token enables this part. Having nothing here enables this, because this is like a knot. This thing, there's no tokens here. It's okay to do it. This one's enabling arc, so it's got to have at least one token there, but the token doesn't move when the transition fires. And this one's a normal arc, but it's got a weight of 3, so it's got to have at least 3 tokens there. In this particular case, it's got 4, so it's okay. So this transition now is enabled because it's got a token there, hasn't got one here, has got one there, and it's got at least 3 there. So that's like having the bullet in the gun. Now if we fire the gun, bang, the tokens move. So that token would move. This one wouldn't move because it's an enabling arc, and this would lose 3 tokens because it's a weighted arc of 3. And this then would gain as many tokens as the weighted arc here. So say we put a weighted arc there of 2, this would gain 2 tokens. If the weighted arc was 1, you only gain 1 token. So if we didn't have a weighted arc on, you would just gain like 1 token. Now going back to this one, so we've got a token there, and let's say 2 tokens there. But this time we've got a token here as well. So what happens now is, because we've got a token here, this is enabled, but this one now blocks this, so this transition can never fire whilst there's a token there. This one's okay, but this one hasn't got 3 in it, it's only got 2, so this one can't fire either. So this transition now, it's like having a gun with no bullet in, because it's not enabled. If you've got some way of getting this token out of here, so you've got some other transition to get rid of that one, and then you could add another one in here. Now it's enabled. If that one wasn't there, again it's not enabled because you've got to have at least 1 here, and if this one wasn't here either, it's not enabled. So you've got to understand how these properties work, and then you can understand then how a Petri can move around as different transitions can fire. So if we look at this one here, it's got, obviously because it's a more in these diagrams here, only one thing can really happen. And here now, there's lots of things can happen. So you can go from this is called a marking. And so from this marking, we could go to a whole gang of other markings, depending on what transition we chose to fire. Let's just have a quick look at that. Just make myself a bit of space here. So in a Petri, we have to have, we tend to call that, say, P1, P2, P3, P4, P5, P6, and say P7. And then the transitions are marked up as well, say T1, T2, T3, T4, T5, T6, and that'll be P8 there, won't it? And that'll be T7. So there are all our markings, places and transitions. And what we can do now is to represent what the current marking of it. So the marking, MK, and there's like 8 places, there's another box with 8 in, that's going 1, 2, 3, 4, 5, 6, 7, 8. And then we can put the tokens in here. So I've got 2 in place 1, I've got 1 in place 2, 1 in place 3, 1 in place 4, none in place 5 and 6, none in place 7, and none in place 8. So that could be my current marking. Now, if we look at this particular Petri, it's in its current condition, it's not very good because we've got a token here, this blocks this transition here. So even if we fired now these 2 transitions here to move the tokens to there and there, we're in a bit of a trouble with this particular Petri because this one's blocking this, and so you can't get rid of this token because this is blocking it, these are enabling it, so you can't fire this transition ever. This particular type of arrangement is called a deadlock. So it's a situation that if you get into, then the whole Petri locks up. So clearly this is a deadlock situation, which would be dangerous. They got some machine and for some reason it just sort of jammed up because it had conflicting things to do. So we don't really need that transition there. So once we've sent some tokens this way, we can't really afford to send any that way. So we have to have a condition of not using T2 that often, because if we get a token there, we block this transition. Now it's in quite good shape. Now with a P4 as a 0, we've now got the potential of P5 and P6. That's 1, 2, 3, 4, 5 and 6. And probably got a 0 there and there. This is the current markings we've got on the diagram. And then what we could do then is we could, for instance, fire T5, and that gives a new marking. I've got this bit outline. So if we fired T5, we still have 2 here. 0, 0, 0. 5 and 6 would go. 5 and 6 would go. And 7 would gain 1. And go to there. So this is what we get if we fired T5. T5 would move us from, this is the current marking, fire T5, we get this new marking here. And so as you fire different markings, you can build up something called a reachability tree. And that shows you then all the potential markings you could have in the system. It could also show you up deadlock situations as well. So if we did fire those, we get a token there, say. Now, what we can do now is, this one now can't proceed until we sort of have to fire T2 then. Fire T2 to get a token there. Now we've got a token in P7 and P4, so we could fire T6, so that one and that one could go. We could get one round to there. We could fire T7, and that could put one back in there. And then we could fire, say, T1, which would put one in there and there. We know now we couldn't afford to fire T2 now. Once we've started this process off, we can't really afford to go that way because it's going to stop and deadlock the system. So then we could fire T3 and 4, get to there and there, and then we could fire P7. Get a token there. Then we could fire T2 and get, say, a token there. Then we could fire those two and we get a token there. Then fire this one and we get a token back here. So we can see every time we go around, we're tending to lose a token. So what we could do is we could put a weighted arc of 2 on there if we want to conserve tokens. So when we got down to there, when it fired again, we get 2 tokens back here. So that's an example of like maybe modifying the Petrinet so as it can conserve tokens. So as it runs, the tokens in the system always remain the same. In which case it'd be a special type of Petrinet. Now the other thing we might want to do is to convert now this Petrinet into an equation. So let's have a quick go at doing that as well. I'm just going to get rid of these tops, bit of a nuisance. Right, so next thing we want to do is, if we've got a Petrinet, we can convert this now into a mathematical equation of number mk plus 1 is equal to mk plus wt. And this is the current marking. This is the new marking. T are whichever transition you happen to want to fire. And W is an incident matrix. Now this is an extra powerful feature of Petris now, that we now have an equation to describe the behaviour of the Petrinet. And because we've got an equation, we can then apply mathematics to this to come up with different designs. State diagrams and graph set can't be easily represented by an equation, but the Petrinet does. So this gives the Petrinet, so you've got this extra power here for this, plus now the fact you can model it by some mathematics as well, and we can use the mathematics to design what are called supervisors, which are Petrinets which behave in certain ways, and in this particular case, say, wouldn't go into a deadlock situation. So one of the things we want to do with Petrinets is design a supervisor to avoid deadlock. And let's have a look at the instance matrix for this. So we write down the number of markings, which is going to be 1 to 8. So we have M1, M2, M3, M4, M5, M6, M7, M8. This is the marking at, say, K plus 1. This is equal to the current marking. That's going to be M1, M2, M3, M4, M5, M6, M7, and M8 at instance K, plus, and now we need a W and a T in there, so not got quite enough room in here, so I'll just rip this out. That's what's handy about a board. Remember, the equation is mk plus 1 is mk plus wt, where w is the instance matrix. So now I'm going to have, in this particular case, I've got 7 transitions. So I'm going to have a matrix here now, and this is going to be T1, T2, T3, T4, T5, T6, and T7. So I'm going to have 7 things down here. 1, 2, 3, 4, 5, 6, 7. So that's 7 different things. And I'm just going to write on here T1, T2, T3, T4, T5, T6, and T7. I'm going to put some rows in as well. So here's our 8 by 7, and now we've got to fill up now this matrix to get our incidence matrix. So if we're thinking about firing T1, if we fire T1, P1 loses a token, so that's going to be -1 in there. But P2 and P3 gain a token, so it's going to be a 1 and a 1 in there. And the rest of it is going to be 0. Look at T2, if we fire T2, P1 loses a token, and P4 gains a token. So they're the ones that go in there. You can see now the instance matrix is quite easy to do. T3, P2 loses a token, and P5 gains a token. If we fire T4, P3 loses a token, and P6 gains a token. If we fire T5, then P5 and P6, P5 and P6 lose a token. 1, 2, 3, 4, 5, 6, 7. There should be 8 of these, shouldn't there? Because there's 8 of them. But this bit, we haven't come to that bit yet, so I was lucky, got away with that. So let's have a look at T5 again. So, but P7 gains a token, so P5 would gain a token. If I fire T6, and P7 loses a token, and P4 loses a token. 1, 2, 3, 4. But P8 gains a token, so that's why I need that extra box down there. And finally, if on T7, this one is T7, and if I add T7, which is the last one now, P8 loses a token, but P1 now gains 2 tokens, because it's a weighted arc here, a 2, it gains a 2. So then if I put noughts everywhere else, and this becomes the incidence matrix now for my Petri net. That's my W matrix for this particular Petri net, and it uses this equation then to describe its behaviour. So the advantage of this now is you could code this into something like MATLAB, and you could use that to say generate a reachability tree or come up with some properties. So what we're going to be doing in the last bit of the course really is, this is like the basic Petri net. We can use this equation now to design what's called a supervisor, which is some trick whereby we can add something to this Petrinet to stop it going into bad states or bad markings. A bad marking, remember, is where we have a token, say, there, there and there. This would be a dangerous situation for us, because once we've got 2 tokens there and there, we can't proceed with the Petrinet, because this one blocks it. So this would be a bad marking, but we could try and design now what's called a Petrinet supervisor. And the Petrinet supervisor now can make use of this equation plus a bit of mathematical analysis to modify this Petrinet to stop these bad markings occurring. And the technique we're going to use to do that is called place invariance. And so the last thing that we're going to look at is next week now, this final bit of the course, is place invariant design. And with place invariant design, we could add something to this Petrinet and we could stop it from going into bad markings. So that's just a quick recap, really. Quick recap of a little bit on basics of Petrinets, properties of Petrinets, incidence matrix of Petrinets. They're the key things that you need to understand. You can probably get them from this quick mini Sunday lecture. And then we can build next week towards a design of place invariance. There's a place invariance video for you to watch, and there's a place invariant design. And then this time next week, I'll do a place invariant example for you, so as you can consolidate on your Petrinet supervisor design, because this is like the sort of end point of the course, and it shows you how you can actually have some problem, mathematically define it, then use some design equations to actually come up with a formal design for your supervisor. And remember, it's also possible to convert a Petrinet into ladder logic as well. So you can also convert this into ladder logic, and so you could then implement your control system. But Petrinet supervisor could be implemented in ladder logic. So that's today's little quick recap. So see you all tomorrow now.